Hi, my name's Dr. Peter Kay, and this is the next lecture in the first year fluid dynamics module. And this lecture is called Buoyancy and Continuity. So in this lecture, I'm going to talk about buoyancy, the formulas for buoyancy and how it relates to bodies that are submersed in the bodies that are in a fluid. We're also going to talk about the concept of volumetric flow rate and mass flow rate, and also I'm going to talk about the continuity equation, which is a very important concept in this field of fluid dynamics. So first is I'm going to talk about buoyancy and the equations that relate to that, and how you can use it to calculate the buoyancy forces on a particular body. So first of all, it's worth saying that a buoyant force is defined as an upward force, which is with respect to gravity. And it's kind of best to explain that with an illustration. So let's consider this square body here, this cube, that's submersed in a fluid. And again, be careful, I'm using the word fluid. That could be a gas or a liquid. It doesn't matter, but let's just say it's a liquid for this case. So we dropped into some water. Now, the hydrostatic forces that are acting on that body, and go back and look at the lecture on hydrostatic forces to remember what those are. But what it tells you is that the force or the pressure increases with the height as you go down in the column of fluid that you're in. So if we're considering all the forces that are acting on this body, we have a force that's acting on the top plane, okay? And the force that's acting on the side plane will start off the same as the top, but it will increase the deeper we go into the column of liquid. And then we have also a force acting on the bottom face, which is equal to that force there. And if we resolve the forces on this body, we can see that because we have the same forces acting on the left-hand side of this body as we do on the right-hand side of the body, these two would cancel out, okay? So there'd be no net force pushing it from side to side. However, if we look at the force that's acting on the top, that is smaller than the force that's acting on the bottom, again, due to this hydrostatic pressure. So there is a net upward force acting on this body, and that's fundamentally what the buoyant force is. And this can be applied to whole bodies that are submerged in the fluid, or partial bodies as well. So a ship still has a buoyancy force, but obviously it's not completely submerged in the water. And the magnitude of the buoyant force can be determined from Archimedes' principle, which says that the upward buoyant force on the body is proportional to is equal to the weight of the fluid that the body displaces, okay? And written mathematically, that is rho g v. So v is the volume of the fluid that the body is displacing, okay? So it's quite a simple formula, really. And obviously, density here is the density of the fluid, not of the object. So what you're really saying is that the buoyancy force is equal to gravity times the mass of the fluid that you're displacing as well. That's another way of thinking about it. So let's consider this example. Hopefully it will illustrate what I've just said. So we have a 5 kilogram mass hanging on this scales. And so obviously you'd expect the scale to come around to 5. However, if we to submerge that mass into this bowl of water, you can see that the reading on the scales it appears to be lighter. It's gone from 5 kilograms up to 3 kilograms. And you can see there's a spout here from this bowl. So as we're lowering the mass in, all the water's spilling out. And if we were to weigh that water, the amount of water that had spilled out, it would weigh 2 kilograms. It'd be the difference between these two. So as I said, it's the way of thinking about it is that although this mass weighs 5 kilograms is displaced, because of its volume, 2 kilograms of water. Okay, and that's the difference. And just to kind of show you what's kind of explain that a bit further, in terms of resolving forces that's acting on the mass. So if we consider this as our mass here, then we've got the force due to gravity, which is pulling it down. That's W, its weight, which is equal to its mass times gravity. We have the tension that's being taken up in the cable, so obviously those two forces are balancing each other out when it's in the air. But when we lower it into the water, we have an additional force which is acting on it, and that's this buoyancy force. And as we said previously, that's equal to rho g times the volume. So if we resolve all the forces that's acting on this 5 kilogram weight, then we've got this. We've got the weight of it is equal to the tension in the cable plus the buoyancy force. Okay, so 1 downward force minus 2 upward forces. So if we kind of wanted to work out the mass on the scale, so we can substitute in for W, mass times gravity, and for the buoyancy it's rho GV. Okay, and if we then kind of say, just to clarify that, so as we said, the mass of water that we displace, the rho V, is the actual mass of water is 2 kilograms. So the mass on the scales went from 5 down to 3, and the difference was 2. Okay, so hopefully that kind of helps to explain what buoyancy force is and how you can calculate it. One quite practical example of this, which is a hydrometer. Okay, and the way that this works is it tends to be a glass tube, normally with a heavy weight at the bottom, some sort of lead weight or sand or something, to keep it upright. And it's put into the liquid, and because of the shape, you know how much fluid this is displacing, so you know the buoyant force that's acting upon this. And if you have a denser liquid, then the buoyancy force will be higher, so it'll be higher out of this graduation will be higher out of the surface, or this will be lower below this will be shallower, it will be nearer the top. Whereas if you have a liquid of a lower density, then the buoyancy force will be less, so it will submerge even more, and the level will be nearer the top of the graduations. Okay, so you can use this to, as I say, work out the gravity of, or the density of your known liquid, and say normally referred to as specific gravity. Okay, which is the density of your unknown liquid relative to the density of water. And as I say, this is quite useful, particularly for amateur winemakers and things. So you can use that to measure the alcohol content of the wine, because as the alcohol content changes, the density changes, and then the readings on this changes.